Everybody. Yeah. So today I'm going to talk about quantization of causal diamonds in 2 plus 1 dimensional gravity, a work that I have been doing with Ted Jacobson. The main part of the work, well, the work is divided in 2 parts. The first part has been published recently, and the second part will come out probably by the end of this week. Um, right. Okay. So we know that there are some challenges in quantizing gravity canonically, such as the nonlinear structure of the constraints in momenta, the absence of local observables, the fact that gravity is perturbatively non-normalizable in dimensions greater than 3, and the problem of time. So it's worth to explore the non-perturbative quantization of gravity in simplified settings, where we may have a better handle at it. So here we consider causal diamonds. And by that we mean 2 plus 1 Einstein-Hilbert gravity with a non-positive cosmological constant in the domain of dependence of a topological disk. So essentially, imagine we have a disk here that will be the Cauchy slice, and you put some spatial metric and some extrinsic curvature, A, where pi is the canonically conjugated momentum. And then for data satisfying the constraints of general relativity, you you consider the maximal development of this initial data, and this will define a space-time. And the class of all such spacetimes is that what you're calling the causal diamonds. We do impose a restriction on the class of metrics, and that is sort of a Dirichlet boundary condition, where the induced metric at the boundary is fixed, such that the total length of the boundary is L. Now, there are two approaches, basic approaches in quantizing a gauge theory. One, it's known as the Dirac approach. And in that one, you first quantize the classical theory, and then you impose the constraints at the quantum level. There's another route where we first impose constraints at the classical level and remove the associated gauge ambiguities. And then we quantize the resulting non-gauge theory. Here we shall explore the second route, which is called the reduced phase space approach. Okay, so similar studies have been considered, but mostly for spacetimes with a closed Cauchy slice, and including works started with Moncrief. More recently, Witten has revived this idea, and Puskar as well. And when you consider a closed Cauchy slice, you typically get a finite dimensional reduced phase space. But we are interested in causal diamonds, in which we have a boundary for the Cauchy slice. So the Cauchy slice is a disk with a boundary. And we find the reason for considering causal diamonds is because we want to better understand gravity in a quasi-local setting, since the notion of subsystems and even the meaning of space-time itself in quantum gravity is quite fuzzy. But in order to have a better handle the problem, we consider low dimensions. So we consider 2 plus 1 dimensions, and with this we can get a better control of the problem without making it too trivial. Because now, unlike the case where the Cauchy slices have no boundary, in this case the reduced phase space ends up being infinite dimensional due to boundary gravitons. Okay, so first we'll quickly discuss this gauge fixing of time by constant mean curvature surfaces, and then talk about how we can solve the constraints non-perturbatively and remove all the gauge ambiguities, and then discuss a little bit about the Hamiltonian generating time evolution between those in this time. And then we will discuss the canonical quantization of the reduced phase space. And we are going to employ a method developed by Chris Isham based on group theory. And then we will talk a little bit about the representation theory and an interesting fact about the spin or the twist of the diamond. Okay, so in general relativity, there's usually gauge associated with both space and time diffeomorphism. However, when there are boundaries on the Cauchy slice, we need to be careful about what happens near the boundary. So in general, if we have a slice and we deform it only around the bulk, only in the bulk, that will generally be a gauge transformation. But if this slice is deformed in such a way that it changes the angle it makes with the boundary, that may not be gauge and instead be promoted to an actual symmetry of the problem. So since we want to explore this gauge fixing of time by constant mean curvature slices, we wish to have this freedom of refoliating the space-time via a gauge transformation. And that is one justification for our choice of the boundary condition of fixing the induced metric. Fixing the metric induced on the boundary. This ensures that all refoliations of the space-time are gauge transformations. Okay. Now, so then there's this very convenient gauge fixing of time by CMC slices. What is a CMC slice? CMC slice is a slice with, well, CMC stands for constant mean curvature, and that means that those slices have a constant trace of the extrinsic curvature. So here KAB is the extrinsic curvature of the slice. We can show that in this class of spacetimes, every causal diamond admits a nice foliation by those CMCs, in particular assuming the non-positivity of the cosmological constant. And so this serves as a universal and non-perturbative gauge fixing for the time, where we choose the so-called York time to be minus the K parameter of the slice. And so as tau goes from minus infinity to plus infinity, those surfaces they sweep through the causal diamond with no gaps and also with no intersections. Okay. Now, the convenience of this gauge fixing of time is that the constraints become particularly simple. So here we are going to write the extrinsic curvature. We're going to separate it into its trace-free part, sigma. So sigma contracted with the spatial metric vanishes, together with its trace full part, which is parameterized by the time parameter k. The constraints of general relativity then translate into those two. The momentum constraint is the statement that sigma is divergenceless with respect to the spatial metric. And the Hamiltonian constraint is this nonlinear equation involving the scalar curvature of the spatial metric and this quadratic term involving the trace-free extrinsic curvature, and this parameter chi, which depends on the cosmological constant and on the time parameter. Okay. There's a very convenient method to solve the constraints, which is called the Licheranovic's method, and it goes basically as follows. So suppose that we start with a pair of spatial metric on the Cauchy slice and traceless divergenceless, sorry, a traceless extrinsic curvature, sigma, so it's a symmetric tensor that satisfies the momentum constraint, so it's divergenceless with respect to the spatial metric, and it also satisfies the boundary condition, so the induced metric on the boundary is the fixed boundary metric gamma. But this pair of quantities, they do not necessarily satisfy the Hamiltonian constraint, which is the complicated one. We call this pair seed data. The idea is that we will apply a Weyl transformation in this data. So we will transform H to some multiple of H, point dependent multiple of H, and also transform sigma accordingly. And the idea is that we can do this this Weyl transformation in such a way that the deformed data by an appropriate choice of this Weyl parameter will satisfy all the constraints. Now, given this specific choice of the Weyl factors with this -2 here, it ensures that the momentum constraint is preserved as we perform this deformation. And if we choose the Weyl factor to vanish at the boundary, then this implies that the deformed data continues to satisfy the boundary condition. The Hamiltonian constraint, which is the nonlinear one, then becomes a differential equation for this scalar field phi. We see here that it's a nonlinear differential equation, so it involves the exponential of the variable phi, and it is an elliptic equation called the Licheranovic's equation. Now, what is interesting about this equation is that if this parameter chi is positive or non-negative, we can show that for any input seed data, the equation always has one and only one solution. And this allows us to characterize the constraint surface on the phase space, so the space of all initial data that satisfy the constraints of general relativity. You can do it as follows. We first note that suppose we consider two sets of seed data that are related by Weyl transformation analogous to the one we considered here. So the metric is multiplied by e to the some lambda, and the sigma is multiplied by e to minus 2 lambda, where lambda is trivial at the boundary. If we use any um, of these two seed data as input for the Lichtenberg's method, they it will output the same set of physical data. So data satisfying all the constraints. Therefore, we can think that the set of all physical data, meaning data satisfying all the constraints, are in equivalence to this in correspondence with the set of equivalence classes uh, of seed data modulo Weyl transformations that are trivial at the boundary. Okay, so this provides a characterization for the constraint surface on the phase space. But we wish also to remove the gauge ambiguities. And we do have a gauge ambiguity associated to, since we have already gauge fixed the time, now we have remaining, it remains to remove the gauge associated with spatial diffeomorphisms. Actually, with spatial diffeomorphisms that act trivially at the boundary. Therefore, we can identify the reduced phase space, which is the space of physically inequivalent classical states, as this set of equivalence classes, where we take this the constraint surface and we further quotient it by diffeomorphisms that are trivially at the boundary. So this is the reduced phase space in this case. We can further identify the set of equivalence classes with the cotangent bundle of the space of conformal geometries of the disk. So note here, so it's the cotangent bundle T star of Q, where Q is the space of conformal geometries of the disk. So meaning any Riemannian metric on the disk modulo a combination of Weyl transformation and the push forward by a diffeomorphism. Both of them acting trivially at the boundary. Well, there's a simple there's a straightforward argument to find out what is this space of conformal geometries in this case. But in view of time and saving time, I'm gonna skip it. I'm just gonna tell you the answer. And the answer is that the space of conformal geometries of the disk is given by this quotient space, where Diff plus S1 is the space of diffeomorphisms on the boundary of the disk, S1, modulo the projective spatial linear group in two real dimensions, PSL2R. Therefore, the reduced phase space is the cotangent bundle of Diff S1 mod PSL2R. And the symplectic form is the natural one associated with the cotangent bundle structure. it's interesting to mention that there is a non-trivial symplectomorphism to the reduced phase space that is most naturally associated to asymptotically ADF. Asymptotically anti-de Sitter spacetimes. And that phase space is, instead of T star of Q, is Q times Q. But surprisingly, there is a symplectomorphism between those three phases. Okay, very briefly, let me mention an alternative approach to reducing the phase space, which is based on a convenient choice of coordinates on the unreduced phase space. The idea is basically, it's based on the fact that due to the Riemann mapping theorem, which is a special case of the uniformization theorem, any metric on the disk, any two metrics on the disk can be related by conformal transformation, as long as the conformal transformation is allowed to act non-trivially at the boundary. So suppose that we have here our Cauchy slice and we have a spatial metric H. And we also have a reference metric H bar, which is fixed. Then there is a conformal transformation, so a diffeomorphism of the disk psi and a scalar field on the disk lambda, such that H is the conformal transformation of H bar. Now, suppose that, so here, suppose it now you also give the extrinsic, the trace-free part of the extrinsic curvature sigma. We can essentially pull back through this conformal transformation, this sigma to a sigma bar on the reference disk, mimicking that form that we saw before with that -2 here. In this way, we have essentially changed coordinates from the usual ADM coordinates, where we have metric and an extrinsic curvature. And now we have a conformal transformation, so a diffeomorphism and a scalar field, together with an object resembling an extrinsic curvature. So it's symmetric and traceless with respect to the reference metric. In those new coordinates, the symplectic form takes a particular format that makes it evident what is the quotient that should be taken, and in order to remove the gauge ambiguities. And one advantage of this method is that since those coordinates naturally reduce to the reduced phase space, they induce a natural system of coordinates. It's basically a natural system of coordinates on the reduced phase space. Since the quantum theory will make statements about observables written on the reduced phase space, in order to interpret the meaning of those observables, it's convenient to have this map between the reduced phase space natural variables to the geometrical variables from the ADM formalism that are more, it's easier to understand their meaning. Okay. Okay, so we found a phase space that is infinite dimensional. And then the question is, what those states correspond to? Especially recalling that there are no local degrees of freedom in 2+1 dimensions. The fact that there's no local degrees of freedom in 2+1 dimension means that the causal the, the interior of the causal diamond is any open set inside the causal diamond is isometric to some open set in ADS spacetime if the cosmological constant is negative, or Minkowski if the cosmological constant is 0. For simplicity here, we will just mention ADS. But since the diamond has, we're also considering diamonds with topologically trivial Cauchy slice. This means that the diamond, any causal diamond in our class of spacetimes, actually embeds as a causal diamond inside ADS3 spacetime. But since the causal diamond is finite, its total shape is unobservable, right? So there are in our phase space, there are causal diamonds that look nice here, uh, look symmetrical, and there are causal diamonds that are a bit uglier. And therefore, this is the points in the reduced phase space are correspond to those different shapes of causal diamonds embedded in ADS3. Moreover, note that if we just specify the location of the corner of the diamond, so a loop embedded in ADS3, this is sufficient to reconstruct the causal diamond, because you can take any spatial slice that is attached to this loop, and then evaluate the domain of dependence of this Cauchy slice, and this will define the causal diamond. So you can think that points in the phase space corresponds to a loop with a fixed length embedded into ADS3 that are the boundary of some spacelike disk. In fact, we can, just for visualization purposes, we can actually construct explicitly a map from the reduced phase space to this embedded loop in ADS3. And we see that indeed, like if we consider different points in the reduced phase space, we get different embeddings of loops in ADS. And for artistic purposes, we can, I'm just showing here what is like a typical causal diamond would look like. So we note that it has those graph-like caustics at the top in general. So, yeah, so this is important to stress. We are not quantizing a single, the single symmetric causal diamond, but the class of all the causal diamonds in 2+1 dimensions with this fixed boundary length. Okay. Now, let us mention here the Hamiltonian that generates time evolution in this CMC time. We can compute it by expressing the action, the Einstein-Hilbert action on shell, so satisfying the constraints, and we can write it basically in a canonical form in terms of variables in the reduced phase space. Oops. The reduced phase space. And whatever is being subtracted from the PQ dot can be interpreted as the is the Hamiltonian. And in this case, we see that it's given by the integral over the spatial slice, over the disk of the exponential of lambda, where lambda is a solution of the Lichtenau's equation that we saw before. The value of the Hamiltonian has a very simple geometrical interpretation, which is that it corresponds to the area of the CMC slice at a particular time. So it's a time-dependent Hamiltonian. Um, but note that despite this simple physical interpretation, the expression of the Hamiltonian in terms of the reduced phase space is actually very complicated because, as I mentioned, it depends on solving the Lichtenau's equation, which is a nonlinear equation and has no closed form solutions. So if one wants to quantize the Hamiltonian at some point, it could be interesting to consider some approximation. And we have a few physical scales that we can play with. In particular, we have the corner length, L. We have the ADS length, L ADS, and we have the Planck length associated to the Newton's constant. Just to mention a simple regime where the Hamiltonian becomes simple, if the boundary length is much bigger than the ADS length, or if we consider very early or late times, and if we restrict to states that are close enough to the symmetric diamond, so that is the one that is the maximal development of the of a Poincare disk, then the Hamiltonian becomes essentially free, meaning quadratic in some momentum-like variables. And so basically corresponds to some sort of collection of free particles with a Newtonian-like energy, kinetic energy. Okay. All right, so this is the only approximation in this talk. So now we will return to non-perturbative analysis. Okay. Okay, now now that we have solved all the constraints and eliminated the gauge ambiguities, we would like to quantize the system. But since the phase space does not have a natural linear structure, so there are no natural global coordinates, we must be careful with the canonical quantization. So just to give a simple example where the naive Dirac quantization procedure may fail, we may even consider a phase space that is topologically trivial, but it's not the typical is not the typical particle on a Rn, but instead let's consider a particle that lives only on the half-plane. The phase space is therefore the positive numbers times the momentum, the momenta R, and we can choose canonically conjugated coordinates x and p. Since they are canonically conjugated, so their Poisson bracket between x and p is equal to 1, we can suppose that we assume that we can the quantum theory is based on representing this algebra with self-adjoint operators x and p on some Hilbert space. Since p is assumed to be self-adjoint, it can be exponentiated for any real number a. Exponential of minus IAP is a well-defined bounded unitary operator, and it will act on eigen values of x as a translation. So it will map an eigenvalue x to x plus a. This means that if x has positive eigenvalues, then it must also have negative eigenvalues. And therefore, we see that this would lead to an improper quantization of this simple case. Okay, so we need to use a slightly more sophisticated method of quantization. And here we choose to employ Isham's group-theoretic quantization. Basically, the statement is the following. We need to find a transitive group G of symplectic symmetries of the phase space, and then construct the quantum theory based on projective unitary irreducible representations of that group. Transitive group, meaning that for any 2 points on the phase space, there's a group element that maps one point to the other. And symplectic symmetry, meaning that the action preserves the symplectic form. The logic is, in summary, the following. Any element C of the algebra of the group induces a vector field on the phase space. And this vector field is a symmetry, generates a symmetry of the symplectic form. Therefore, to that vector field, it's associated another charge, essentially, which we call Qi. The Poisson algebra of these charges is homomorphic to the algebra of G. Actually, it's homomorphic only up to possible central extensions. But if it happens that there is a non-trivial central charge in this Poisson representation, we can always go back and essentially extend the group G and repeat the procedure, and then we'll find that the Poisson algebra will actually be homomorphic to the algebra of the group of symmetries. So we will assume that there are no non-trivial central charges appearing here. The transitiveness of the group implies that this set of charges is complete, meaning that the specification of the value of all the charges uniquely specifies a point in phase space, up possibly to a discrete ambiguity. And this consequently means that any observable can be locally expressed as a function of those canonical charges. Okay, so since with this procedure, we have a complete set of charges representing this symmetry, and that is also algebraically closed, then we can apply the basic principle of canonical quantization and replace this Poisson algebra by an analogous algebra of self-adjoint operators on the commutator algebra on some Hilbert space. So this is the summary of Isham's quantization scheme. And therefore, we need to find such a group of transitive group of symplectic symmetries. On the phase space. So the configuration space, the configuration space is a homogeneous space for the group Diff plus S1. So it's natural to start with the action of Diff S1 on the configuration space, where it acts on the equivalence classes by composition inside the equivalence class. Um, and since the phase space is the cotangent bundle, the points P on the phase space can be identified with one forms at points of the configuration space. And therefore, this action on the configuration space leads to action on the cotangent bundle, where we simply we consider the pullback by the inverse map. This action can be shown to be symplectic. However, it does not act transitively on the phase space, right? It only acts horizontally, basically. It has no way to move points along the fibers of the cotangent bundle. So we need to enlarge this group by adding also some sort of vertical action. And Isham has also proposed a general procedure to perform such an extension. It's basically as follows. Suppose that we have a group K acting on the configuration space. In this case, our group K, the candidate for the group K was Diff S1. Okay, so what you have to do is to find the representation of K on a vector space V, such that at least one orbit in V is homomorphic to the configuration space Q. Okay, so suppose here that we have the vector space V and we have this configuration, the configuration space Q that has been embedded as a K orbit into this vector space. Therefore, points on the configuration space can be identified with vectors on V, and also tangent vectors at points of Q can be also identified with vector in V. Therefore, if we consider any dual vector W in the dual space V star, it induces a one-form field on Q, right? Because we can simply take this W and we act on C at this point, and that returns a real number. And so this defines a one form at this point, and in fact, it defines a one form at every point of Q. So it's a one form field. Okay, and so having this one form field, we define the momentum translation simply by translating P, which is also one form at points of Q, at the base point. And so we pointwise translate it by W. So this defines a vertical action, which also happens to be a symplectomorphism. And more importantly, it combines with the previous horizontal action to form a transitive group of symplectomorphisms. Okay, so let's go back to our case. We had the natural choice for the group acting on the configuration space was Diff S1. But we could not find any representation of this group with this property of having an orbit isomorphic to the configuration space. However, it turns out that the coadjoint orbit of the Virasoro group, which is an extension of the Diff S1, is a central extension of Diff S1 by R. On its dual Lie algebra, Vira star, which is the dual Lie algebra of Virasoro, it does have an orbit isomorphic to the configuration space. And since the Virasoro group is just a central extension of Diff S1, it also has a natural action in the configuration space, where the central element acts trivially. The central, it acts trivially. And so we could just as well start with the Virasoro group being this group of symmetries on the configuration space. And the representation that we will use to construct the momentum translations will be based on the vector space Vira star, the dual of the Virasoro. Therefore, the group to be quantized will be chosen to be the semi-direct product between the Virasoro group, acting horizontally on the phase space, and the double dual of the Virasoro algebra, acting as momentum translations. Okay, let us just see how the algebra looks like. Now, the algebra of G has a semi-direct sum. Is a semi-direct sum between the Virasoro algebra coming from the Virasoro group and another a commutative algebra that we call Vira-C. That comes from the momentum translations. So the choice of notation here seeks to indicate that while this algebra is isomorphic to the Virasoro algebra as a vector space, it does not have the same algebraic structure, but instead it's commutative, since the group of momentum translation is abelian. Okay, so then we have this algebra, and the algebra of Virasoro is a central extension of the algebra of Diff S1, and the algebra of Diff S1 can be identified with elements of the algebra of Diff S1 can be identified with vector fields on S1. Okay, so then the elements of the algebra of Virasoro can be identified with a vector field on S1 together with another real number. And there's a convenient basis, a Fourier basis, where we decompose those vector fields in Fourier modes. So for the configuration translations, so things coming from the Virasoro part of the group, we define the generators L, N, where the DPS1 part is this Fourier mode, and the corresponding central element we call R. And similarly, we have momentum translations, and if we take the element of diff S1 to be Fourier mode, we call that K, and the corresponding central element we call T. And then in this basis, the algebra gets this particular form. So we see here that for the algebra associated to the configuration translations replicates essentially is exactly the Virasoro algebra. The algebra of momentum translations is commutative, and there's also a mixed bracket between the momentum and configuration translations generators. Okay. Okay, now we need to realize these algebra on the phase space, and then right, as some Poisson algebra of charges, of Hamiltonian charges. And the charges generated by the L's, which are the configuration translations, they look like momentum, right? So they translate horizontally on the phase space. So we call those P. The charges generated by the momentum translations, they look like a position. So we call those Q. In this realization, the central charges R and T are realized as constants on the phase space, with the values 0 for R and 1 for T. Therefore, the Poisson algebra reduces to this form here. So we see that the central element of the Virasoro actually went away. So we went back to the algebra of diffeomorphisms for the configuration translations. But the net effect of this extension from Diff S1 to Virasoro was to introduce a central element in the mixed bracket between the Q's and the P's. So we still have a central element here. Interestingly, this algebra is actually the BMS3 algebra, which corresponds to the algebra symmetries of 2 plus 1 asymptotically flat spacetimes at the no infinity. Okay, so let us now just discuss a particular observable in the theory, which is interesting, and that is the P0 charge. Now, the P0 charge is associated to the uniform diffeomorphism, so the constant mode of the constant Fourier mode, and therefore it generates the SO2 subgroup of Diff S1 as a subgroup of Virasoro. And it therefore it can also in the ADM formalism, it can also be interpreted as the generator of diffeomorphisms that act as isometries of the corner. And therefore, P naught can be interpreted as the spin of the diamond. Okay, and but it can also be interpreted geometrically as corresponding to the twist of the corner of the diamond. So P naught is related to the twist by this ratio involving the length, the total length of the loop, and the Newton's constant. And just as a reminder, what is the twist? The twist is basically the integrated torsion along the loop. So if we have a loop embedded into a three-dimensional space, and we consider a frame that is transported along this loop with one vector aligned with the tangent direction and another vector aligned with the acceleration, then the rate of rotation of this frame as you move along the loop is the torsion, and the integral of the torsion along the whole loop is the twist. It has another nice interpretation as being the holonomy induced on the normal bound of the loop. So if you take any frame, any frame, and you parallel transport it along the loop, when this frame comes back to the original position, it will be boosted with respect to the original one. And this hyperbolic boost angle is equal to the twist. Okay. I'm almost finishing. Um, how much time do I have?
You have, yeah, you have like 5 minutes. We can take 5 minutes.
Okay, okay, I'm almost finishing. All right. So, um, okay, so then we can construct the representations of this group. Since the group is okay, the quantum theory is based on some projective, unitary, irreducible representation of this semi-direct product between Virasoro with this abelian Virasoro algebra. And therefore, we can in principle apply Mackey's theory of induced representations. Modulo possible issues with the infinite dimensionality with the algebra, which we will ignore here. The conclusion is that the representations are given by wave functions living on some coadjoint orbit of Virasoro with extra internal indices in unitary irreducible representations of the corresponding little group associated to that orbit, right? So the subgroup of Virasoro that fixes any particular point of that orbit. One such orbit is the configuration space itself. So this seems to be the most natural choice. Therefore, if we choose the orbit to be the configuration space, GPS1 mod PSL, the corresponding little group will be PSL2R times the central element, which of course is included in any little group. From the classical values of the Casimir operators, this choice of orbit is compatible with T being 1. And if we impose R to be 0, that selects the trivial representation for the central part of H. This means that the quantum theory should be based on wave functions living on the configuration space with internal labels in unitary reducible representations of PSL to R. We can look at the algebra, but let's skip this. Okay. The final thing, going back to the spin, we can now analyze what is the spectrum of the spin in this quantum theory. And we see that all the Pn's and Qn's act as ladder operators for P naught. And we can show that this implies that the spectrum of P naught is of the form S plus N, where S is some fixed real number in fixed real number in fixed real number between 0 and 1, and N is an integer. Using the time reversal symmetry of the Hamiltonian, we see that S must be actually 0 or 1/2. However, the 1/2 case would be the odd case where you do a full rotation and the wave function changes by a -1. It's a projective representation. And you can in fact show that at least if we choose the orbit to be the DPS1 mod PSL, as we mentioned before, this actually selects the S equal to 0 case. Therefore, the conclusion is that the twist of the corner, the corner loop, must be quantized in integer multiples of this ratio involving the Planck length to the corner length. In particular, notes that if we consider that the corner of the diamond has a length that is much bigger than the Planck length, then the steps between those levels go to 0, and then we recover the classical limit in which the twist can be is a continuous parameter. Okay, let's skip the Q charges, and then that's just the summary. So we have considered 2 + 1 pure gravity with a non-positive cosmological constant. in the domain of dependence of topological disks with a fixed induced metric, using a constant mean curvature for time, we solved the constraints and eliminated the gauge ambiguities, and found that the reduced phase space is the cotangent bundle of Diff plus S1 modulo PSL2R. The CMC, the Hamiltonian generating evolution between CMC slices can be interpreted as the area of the CMC at the particular time, but that is a complicated function on the reduced phase space, which can be simplified in some regimes. Applying Isham's group-theoretic method, we can quantize the system based on the BMS3 group, and then Mackey's theory gives that the representations are carried by wave functions on coadjoint orbits of Virasoro with labels in unitary irreducible representations of the corresponding little group. And we found that the spin, which is related to the twist of the, or I should say, the twist of the corner of the causal diamonds is quantized in integer multiples of 16 pi square Planck length over the length of the loop. Okay, here are some open questions, but I will leave it here and then let you ask any questions. So thank you.
Let's thank let's thank Andy for this Rodrigo for this amazing talk. This is a really wonderful talk, and it's time for questions. So if anybody has any questions, please go ahead, unmute yourself, and go ahead. Sorry, is anybody asking questions? Come on, don't be shy. You can ask questions. Unmute yourself. All right, then I'll ask a couple of questions, I guess, if that's all right. Yeah, great talk. So, I'll ask some basic questions like in the beginning, like not getting into too much details. I'll read you the article actually, which is, I guess, that part 2 is coming out pretty soon, right?
Yes, part 2 is probably coming by the end of this week or perhaps early next week.
Cool. Okay. Yeah. So one thing I'm kind of interested in was, you mentioned like this two scheme of quantization, right? The usual scheme of quantization is the first quantize and then impose the Gauss law constraint as like, constant on the wave functions. And then the second one you mentioned was like first take the quotient, go to the reduced phase space, and then quantize. So at the beginning, at the very beginning, like in the slide 1 or 2, you had this commutative diagram.
Yes.
So what's the difference? Is that diagram like commutative, or like is there some sort of?
No, that is a great question. It's
Yeah, exactly, this one.
yeah. So it's completely unclear whether this diagram commutes. In fact, there are some evidence, including some papers in quantum gravity.
Right.
I can give you the reference. I think is a paper by Horowitz, if I'm not mistaken, that actually showed that in some cases they do not commute. So that is why I didn't put here the same quantum theory,
Right.
but so it's not guaranteed that you get to the same quantum theory.
Ah, I see. Okay, so that's why you put like one top, one bottom, so they could be different.
Yeah. So in principle, yeah, it could be the same. It's just not guaranteed as far as I know.
See. So
So here we just focus on the second one.
Right.
not because we think it's better,
I mean, it
but
seems natural to me, the second one, like first going to the orbit space and then like quantizing, But
yeah, right. Yeah, I
but
agree to it. It's because you make sure that you completely remove, you make sure that you're satisfying all the constraints and removing the gauge ambiguities.
right, yeah,
Therefore, you're just quantizing a theory that does not have gauge anymore, right? You're just
right,
quantizing the physical degrees of freedom.
right, yeah. So that's very interesting. So I was wondering, like, is the difference between some sort of operator ordering, like, in these two roots, like, in these two, is there like what is the difference exactly? Is there some operator ordering? I'm not sure. Like, yeah,
I mean, the difference, well, yeah, in one sense, for example, when you impose the constraints at the quantum level,
right,
it may be that the constraints are, I mean, often the constraints are nonlinear functions of
correct,
the
yeah,
basic variables that you use to quantize. So by imposing the constraints at the quantum level, it means that you first promote the constraints to an operator,
right,
and then you restrict to physical states that are annihilated by those constraints,
right.
at least in a weak sense. So in finding this operator, there is indeed, in general, some operator ordering, right?
I see. Okay,
Um,
nice, nice. And okay, and the second question was like, what happens like if you consider like de Sitter, like lambda positive? Like, is that you already are you thinking about that, or is it like some difficulty with that?
yeah, so we chose, so there were basically 2 points where this condition appeared. One was to to prove that the CMC foliation
Ah,
is nice on all this class, we use that lambda is non-positive.
yeah,
And we have also used this later
for the Lichner-Weiss equation,
in the
right?
Lichtenog's equation
Okay, I
because we
see.
wanted chi to be non-negative.
Right,
So uh, we also use this.
I see. So if you have like lambda positive, this actually solution can become non-unique, right?
Yeah, in principle, we have not proved that is the case. We have just proved that you have just proved the statement for this case.
Right,
Uh, Now, one thing that is a bit different. So we have, for example, made lots of I have some pictures, like what is the typical causal diamond.
right.
In the case of a positive cosmological constant, um, the domain of dependence of a finite disk is not necessarily finite region.
I
So
see.
there's also that difference.
I see. Right. So I think we got another question. So
Yeah, right. Is it all right if I just ask a question? I missed a lot of the talk actually, but I just
yeah, go
wanted
ahead.
to ask about that diagram that was there earlier.
Which one? The, the quantization one?
Yeah, this one. So actually, it just kind of looks somewhat reminiscent of like refined algebraic quantization, where you have like some kind of an auxiliary Hilbert space, and then you impose the constraints. Then you take the subspace of the Hilbert space that actually satisfies those constraints, and that's the physical Hilbert space.
Yes.
Yeah. So is it something like that? I actually missed the talk. I don't exactly
Yeah, yeah, yeah,
asking.
yeah, yeah. This would be this approach going here. Yeah, the one you describe is known as the Dirac approach,
Yeah, yeah,
where
yeah.
basically, right, you first quantize it, ignoring the constraints, and then we impose the constraints at quantum level by saying that the operators associated with the constraint annihilate the physical states, so you restrict to the subspace, and also that the physical operators are those that commute with the constraints, at least in the weak sense, meaning at least within when you sandwich between physical states.
Oh, right. Okay.
So this is one approach. This is not the approach that we used in this work. The one that we used was the second approach, where we first imposed the constraints at the classical level, removing the gauge ambiguities, and then quantize the resulting theory, which no longer has any constraints.
Oh, I see. Okay. Thank you.
Do you have more questions? All right, if not, then, let's thank Rodrigo again for this wonderful talk, and we'll see everybody next week.
Yeah, thank you very much for the invitation.